Welcome back, everybody. Today we are going to begin Unit 2, the derivative. Let's begin with the definition of derivative. Derivative of a function y equal to f of x, like the one I have shown here in the graph, which is the function y equal to f of x. The derivative of the function y equal to f of x with respect to x is denoted as, we write derivative like this. We write y prime, or we write, if it is a function, for the function we write f prime x, or we write dy over dx. These are all derivative. Y prime is the derivative, f prime x is derivative, dy over dx derivative. They are the different form of denoting the derivative. These are the different notations. And the derivative is defined as this quantity here, dy over dx is equal to limit as h approaches to 0 of f of x plus h minus f of x over h. So this is the definition of derivative. This is also called the limit definition of derivative. We are studying this derivative in Unit 2 because it has some important applications. Like the first one is, the derivative is used in the measure of rate of change of quantity. When I say rate of change, like if I'm talking about the atmospheric pressure with height, when height increases, what happened to the atmospheric pressure? How does it change? So those type of change are measured using derivative. That's one application. Using the derivative, we can also find where the function is increasing, where the function is decreasing, or where it remains constant. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. And if the derivative is 0, the function remains constant. So derivative is used in the calculation of, or to indicate where the function is increasing, decreasing, or it will remain constant. Next, derivative, we use derivative to determine the maximum or minimum value of the function. If you want to find some maximum or minimum value of the function, then we can use derivative. Similarly, the last application that we'll see in our course is to determine the equation of the tangent line or normal line to the curve. If I want to find the equation of tangent, like the one it is shown here in the graph, this is the tangent line. If I want to find the equation of this tangent line at this point, then we can use derivative to find the equation of the tangent line. So these are some of the wide applications of derivative, and this is the definition to find the derivative. If you are asked to find the derivative of the function, then we'll use this definition to find the derivative. So this is the brief introduction to derivative of a function. Example, using the definition, that is, this is the definition, we have to find the derivative of the following functions. There are two functions here. We have to find the using the definition, we have to find the derivative. So let's work on part A. So in part A, we have the function. Let that function be square root of x. Let's write like that, because we have y equal to f of x, which is same as f of x equal to square root of x. Now, what we know is the derivative is equal to dy over dx is equal to limit as h approaches to 0. Then if you look at the definition, limit as h approaches to 0, we have f of x plus h. This is our f of x, so f of x plus h will be square root of x plus h minus f of x. F of x is square root of x divided by, in the denominator there is a h. So that is the definition. Now we have to evaluate this limit. If we evaluate the limit, we will get the derivative. We already know how to evaluate the limit. This one involves the radical function. You can see there's a square root. So if you are evaluating the derivative involving the radical function, we need to multiply by the conjugate. So let's do that. Multiply both numerator and denominator by conjugate. Square root of x plus h plus square root of x divided by square root of x plus h plus the square root of x. So we multiply by the conjugate because we are evaluating the limit involving radical. That's what we know from our first chapter. So this is equal to limit as h approaches to 0. Now, in the numerator, if you use the formula, which was, if you remember that formula, factoring formula, a plus b times a minus b is equal to a squared minus b squared. Now, if I use that formula, see, it is like a minus b times a plus b. So if I multiply, it will be the square of the first. If I square the first, it will be x plus h. Minus, if I square the second is squared, b squared is there. So if I square the second, that is x. And in the denominator, you have h multiplied to that quantity. H multiplied to square root of x plus h plus the square root of x. Now, if you look at the numerator, x get cancelled. So we are left with the limit as h approaches to 0. In the numerator, we have h divided by, in the denominator, we have h times the square root of x plus h plus square root of x. Now you can again see h divided by h is 1. So you can divide that. H divided by h is 1. Now you can perform the direct substitution because you don't have that h which was there in the denominator that was causing 0 there. Because if you try direct substitution here, when you plug in 0, there will be 0 in the denominator. Now h get cancelled, so no more 0 in the denominator. So that will be equal to, if I substitute h equal to 0, you will get 1 over, now you can see here, it's a square root of x plus 0, which is square root of x, plus the other one is the square root of x, which is equal to 1 over 2 square root of x. So the derivative of square root of x is 1 over 2 square root of x. Now what I want you to do is, I want you to write this as a formula, derivative with respect to x of square root of x. We just found the derivative, d over dx is the derivative. Derivative with respect to x of square root of x is equal to 1 over 2 times the square root of x. So this is a formula that you need to remember. This is your formula. So this is how we can find the derivative of the function using the definition. Okay, now let's work on part B. So in part B, my function is this. F of x is equal to, y is equal to 1 over x. So my function is 1 over x. Now the derivative will be dy over dx is equal to, I'm using the definition. So when I'm using the definition, I'm using this definition here. So that is limit as h approaches to 0. Now we have f of x plus h. So that is 1 over, my function is 1 over x, but I'm looking for f of x plus h. So it will be 1 over x plus h. Then minus, we have f of x. F of x is 1 over x. And we have to divide that by h. We have to divide that by h. So if I simplify this, dy over dx is equal to the limit as h approaches to 0. Now, if we simplify this fraction, if I simplify the fraction, it will be x minus x plus h divided by h times x plus h multiplied to x. Let me, yeah, check it. Yeah, that's correct. So that is good. So when you simplify this fraction, this is what you'll get. So this is equal to the limit as h approaches to 0. In the numerator, you have x minus x. When I distribute this negative sign, it will be minus h divided by, in the denominator, we have h times x plus h multiplied to x, which is equal to, in the numerator, you can see this x get cancelled because one is positive, other one is negative. Then we have the limit as h approaches to 0. In the numerator, I have a negative h. And in the denominator, we have 8 multiplied to x plus h multiplied to x. Now let's see what we get in next step. So in next step, this is equal to limit as h approaches to 0. Now when you look at these two values here, you have h and here is negative h. So negative h divided by h, those two will get cancelled and you'll get a negative 1. So in the numerator, you have a negative 1 over, in the denominator, x plus h multiplied to x. Now when h approaches to 0, h approaches to 0. So when you plug in h equal to 0, this will be negative 1 over x plus 0 is x, multiplied to x is x squared. So the derivative of 1 over x is negative 1 over x squared. That is also a formula that you need to remember. So remember that the derivative with respect to x of negative, not negative, derivative with respect to x of 1 over x, this one, derivative of 1 over x is negative 1 over x squared. Negative 1 over x squared. So that is the formula that we need to remember from this example. Okay, that is the end of example part B. Example, using the definition, find the derivative of following function. Here is the function. We have to find the derivative of y equal to x to the n. And there is a hint given, so we may use this hint in a little bit. So let's begin. Our function is f of x equal to x raised to n. That is the function given to us. Now what we have to do is, we have to find the derivative. Now, the derivative dy over dx is equal to the limit as h approaches to 0. Then we have the function at x plus h. This is f of x. F of x is x to the n. So x plus h will be x plus h raised to n minus f of x. F of x is x to the n. And we have to divide that by h. That is the definition. Now, after we use the definition, you can see here we have x to the x plus h to the n. But what is x plus h to the n? They have given this result for you. So in place of x plus h to the n, we are going to use this result. So let's write that. Limit as h approaches to 0. Okay, x plus h raised to n is combination of n objects taken 0 at a time. That is the meaning of that. n0 x to the n, then plus n1 x to the n minus 1 multiplied to h, this one, n1 x raised to n minus 1 h plus n2 x raised to n minus 2 h squared. Then this will continue all the way to, let me write the last one. The last one is nn x h raised to n. Then we have to divide all of these by h. So what I did is I just used the expansion or the expanded form of x plus h to the n over here. So that's the value of x plus h raised to n up to here. Then also, if you look at this carefully, at the end, there is minus x to the n. Minus x to the n. So I use this value which is given to us into our definition. Now let's simplify this one. So in order to simplify this, we'll use some known fact of math that we have. Now, the combination of n objects taken 0 at a time, the value of this one is 1. n0 is 1. That is something you need to remember. We are not going to look at the proof of that in our course, but just remember n0 is 1. So 1 times x to the n is x to the n plus the second one, combination of n objects taken 1 at a time, that is n. Then you have x to the n minus 1, h. Then plus, next one, I don't want to simplify that. I'm just writing it. H squared plus the last one is nn h to the n minus x to the n, all divided by h. Now, if you look at the numerator, you'll see a magic there. Here is x to the n, here is x to the n. One is positive, other one is negative. So they get cancelled. They get cancelled. So in next step, if I simplify next step, let's simplify this. H approaches to 0. Now this is a common denominator. H is the denominator of this first term. H is the denominator of the second term. It is the denominator of all the term in the middle, and also it is the denominator of the last term. So if you look at it carefully, we have n x to the n minus 1. Then here is a h divided by h. That's a 1. So just that much. Plus you have n2 x raised to n minus 2. And here we have h squared. There are 2h there. Divided by 1h is just 1h. Then plus, we'll continue like that. And the last one is nn. You have h raised to, if you look at this one, here is h raised to n. You have n of them, and you are dividing by 1, h, which is h to the 1. So the power will reduce by 1. So h to the n divided by h is h to the n minus 1. Now we are almost done. Let's see what we get. It looks crazy, but it's not difficult. So we can say we are looking at the derivative with respect to x of x to the n. That's what we are looking at. And we get this value here. Now h approaches to 0. If you plug in h equal to 0, what happened? Here is h. So if you plug in 0, 0 raised to whatever number is that, that's a 0. So this term is 0. And then here we have the h. So if you plug in 0, that will be 0. And here we don't have h. So that will remain. That is x, not x, that's n. N times x raised to n minus 1. So that is the derivative of x to the n. So derivative with respect to x of x to the n is equal to n multiplied to x to the n minus 1. The result that we obtain here is a very important formula in calculus, and this is called the power rule. This is called power rule. So we use the definition of derivative to derive the power rule. Please highlight this. This is very, very important, and we'll be using this in all upcoming sections. Example, using the definition, find the derivative of following function. So here is the function, which is y equal to e to the x, and they have also given a little hint that we'll be using later on while solving this problem. So let's begin here. Here my function is e to the x. Now I need the derivative. So I can write the derivative as dy over dx, or I can even write f prime x. And you know that the definition is limit as h approaches to 0, f of x plus h minus f of x divided by h. So that will be equal to the limit as h approaches to 0. F of x is e to the x. So f of x plus h will be e to the x plus h minus f of x is e to the h divided by h. Okay, now let's go to next step. So this implies the derivative, I'm writing it as f prime x is equal to the limit as h approaches to 0. Now e to the x plus h, meaning of that is e to the x multiplied to e to the h, minus there is e to the x divided by h. So you can see over here we have e to the x plus h. So e to the x plus h is same as e to the x multiplied to e to the h. So I break that. So we get in next step limit as h approaches to 0. In these two in the numerator, e to the x is a common factor. And we get e to the h minus 1. In the denominator, I have h. See, I factor this e to the x out. Now we are calculating the limit as h approaches to 0. So h is the variable. So wherever you see h, that is the variable. But this one is a constant. For this problem, e to the x is a constant because the only thing changing here is h. So because this is a constant, you can take it out. So if you use the constant multiple rule of the limit that we have studied in chapter 2, you can factor that out. Then you get limit as h approaches to 0, e to the h minus 1 over h, which is equal to e to the x multiplied to, now this limit as h approaches to 0, e to the h minus 1 over h, look here, they have already given that this is equal to 1. This is a well-known fact in calculus. This is always equal to 1. If you try to evaluate this limit using numerical method or tabular method, you will see that it will be 1. So that is 1, which is equal to e to the x multiplied to 1 is e to the x. So this is yet another important formula. The derivative with respect to x of e to the x. The question was e to the x. We are calculating the derivative of e to the x. My answer is also e to the x. Derivative of e to the x is also e to the x. That is very, very important formula that you need to remember. And we derive this using the definition of derivative over here. Derivative with respect to x of e to the x is e to the x.